Okay, so give you a quick review for previous class. We talk about we have a vacancy mediated solute diffusion in FCC structures. So we have a host atom and we did have a dopant at the substitutional site and also solute atoms. So when we want to discuss the diffusivity of these solute atoms, then based on the vibration frequency or jump frequency, we can simply classify into two cases, right? And the first one, case one, is we have a strong correlation between the solute and the vacancy, means they switch or exchange the location always. So the gamma prime SV is much larger than the gamma prime the host atom surrounding solute jump in vacancy. Then the slowest one will be the host atom jump in vacancy. So based on this, the limited step to drive this solute atom diffuse through this FCC structure actually is the gamma is instead of this gamma prime between the SV, because this is this jumping process, even though the gamma prime is quite fast, but there's no contribution on the diffusivity of solute atom, right? Because you can see the solute atom jump to left-handed side, jump to right-handed side, nothing. Have no contribution to the diffusivity of a solute atom. But however, the gamma prime Vs, which means the host atom surrounding solute jump into vacancy, will be the limited step to lead the diffusion of the solute atom. So when you try to write down the ds, the diffusivity of the solute, and bind it with vacancy, then it will be proportional with gamma prime Vs. And alpha A is a geometrical factor related to the crystal structure. And when we try to formulate the diffusivity of the solute, and the idea would be what? Would be the diffusivity of the solute atom binded with the vacancy. But don't forget, also need to terms the probability. You can find this pair, this solute and vacancy pair. Okay? And because they are a pair, they are a group, right? So the XVS actually is the probability to finding a vacancy times the 12. The 12 is due to they are the group. So if you put the solute atom at the center, and the vacancy can be at the nearest 12 location, right? Nearby the solute. So based on this, they are a pair. So you need to consider the solute can be, or probably on the other words, you can consider that if you put the vacancy at the center, and the solute can be show up at 12 nearest locations, right? So as long as the host surrounding solute jump into the vacancy, and this will drive the diffusion of solute, right? So based on this, the solute can be moved or diffused through 12 different directions. So based on this, we can easily formulate the diffusivity of the solute, and this is the diffusivity of solute binded with a vacancy, so will be equals to gamma or alpha A gamma prime Vs is the same with this one. And the 12 will be equals to 12, and the probability to find a vacancy would be proportion with this term is the vacancy formation energy, and also the vacancy binded with the energy to the vacancy binded with solute atom. So will be the PV. Okay. So regarding to the case 2, the difference would be the order between the gamma prime Vs and the gamma prime Sv. So in the case 2, we have a strong correlation between the host atom near neighboring solute jump into the vacancy. This one gamma prime will be much larger than the gamma prime between Sv. But based on this description, the gamma prime Vs, even though gamma prime Vs is quite high, which means this host atom neighboring solute atom will jump into vacancy, and this will jump into a vacancy, and so on. So you can observe the circling effect of this host atom neighboring solute. We can observe the circling stuff, right? But this kind of jumping process has no contribution to the divisibility of solute, but as these figures, you can observe this circling stuff, but solute still stay at original location. So when or which what type of atomic jumping process will drive this solute diffuse through this FCC? The limited step would be what? Would be the gamma prime between solute and the vacancy happens. So I give you some examples. Because the gamma prime Vs is much larger, so it's all probably you can observe the circling stuff for a very long time. But next, you can observe a jumping process between the solute and the vacancy. So that will lead the solute will be jump to the left-handed side, and vacancy will be show up at right-handed side. So the figure will be like this. And the following jumping process will be the same, right? The host atom neighboring solute will jump into the vacancy, so also will be the circling events, and also have no contribution to the divisivity of solute. And next time jump probably is also the jumping process between the solute and vacancy. So you can observe the solute jump to left-handed side to here, and the vacancy jump to right-handed side. So and after a while, the circling events always occurs. So based on these figures, you know the solute diffused from this location and now successfully diffused to this location in FCC structure. So the limited step jumping process actually is the gamma prime SV, would be the limited probability. So based on this, you can successfully write down the divisivity of this solute binded with vacancy will be proportional with gamma prime SV. And also alpha B is geometrical factor related with crystal structure. And this is the divisivity of the solute, right? But the question here is the divisivity of this solute inside this FCC structure will be affected by the divisivity of the solute binding with the vacancy, and also this pair, the fraction or the probability to finding the pair of this solute and the vacancy. So the same idea, so you also can find this 12 PV, and also just copy fill out all the informations, so you can get the divisivity of the solute. And regarding to the 12, actually, some people want me to explain more, so probably I hope I can draw something. This is the vacancy, right? And because the coordination number for FCC is 12, so if you have a solute because in this case, solute and vacancy is a group, right? So the solute always have a strong binding energy or binding with the vacancy. So under these situations, the solute can show up in 12 different locations nearest vacancy, right? So because they always jump together, so how this solute diffuse through this type of mechanism? As long as what? As long as the atoms, the host atom enabling solute jump into the vacancy, then the vacancy will be show up here, and because there's always they are a group, right? So they will lead the solute diffuse, right? So based on this, even though the probability to finding the vacancy is this probability, but because they are the group, so the solute atom can show up into 12 different locations. So in that case, the solute finally can go or move away or diffuse through to 12 different directions. Okay, so that's just for your reference. So next, we are going to give you a summary and focus on the vacancy mechanism. In previous slide, in previous sections, we talked about vacancy mediated mechanism. In that case, all the atoms belongs to host atom, so the diffusivity of the host atom can express like XV dVF. But if you dope some dopant or solute atom at the substitutional site and want to understand or estimate the diffusivity of this solute, based on the previous slide, we know that the diffusivity of a solute is expressed like this, and the gamma prong here can, depending on the case, belongs to case 1 or case 2. You can put the limited probability, the gamma prong of with limited probability. But based on this description, if you focus on the explanation term, gamma prong also is a migration energy, so you combine the explanation temperature dependent term together, so you find that the explanation term actually included the formation energy, vacancy migration energy, and the binding energy. And as you know, the binding energy is negative, so this plus a negative term, so after summary you got the smaller value here, right? So explanation minus smaller value, so the diffusivity of solute for sure will be larger than the diffusivity. This dot here, because this is a negative term, okay? So let's explain why when you do some dopant stuff, you want to increase the electrical conductivity or thermal conductivity of your materials, and some people will suggest you to end it a dopant. You need to dope a solute atom at the substitutional site. Then in that case, the diffusivity of solute atom will increase, and which means implying that the corresponding material properties will increase as well. Okay, so let's move to, so we finished the first part regarding to the atomic diffusion mechanism, and the second part, let's move to the second part, will be talk about, because in first part we put more efforts on different atomic diffusion mechanism and accompany with the different crystal structures, and want to use to estimate the diffusivity of host atom or solute atom, right? And the materials we will is focus on the metal materials. But how about if we change the materials to ionic solid materials? So can you modify or estimate the diffusivity of an ion or cation in ionic solid materials? So in ionic solid materials, so first of all, your textbook focus on the second atomic diffusion mechanism, which is the vacancy-mediated diffusion mechanism in ionic solid materials. So in this part, we focus on the vacancy mechanism. So in this case, we are going to introduce two different vacancy formation mechanisms in ionic solid materials. The first one we call is a Ch4 defect, and the second one is Frankel defect. And this is then we are going to extra added some dopant to this ionic solid materials and show you how to modify the diffusivity of the cation and anion under this extrinsic and non-stoichiometry effect or conditions. So let's move to the first part is in ionic solid materials, there are two commonly seen vacancy formation mechanism. The first one we call it is a Ch4 defect, which means that we have a pair of cation and ion vacancies be created inside your ionic solid materials. So let's take a potassium chloride material as an example. You can observe this larger white ball is the chloride ion, and the small black ball means the potassium ion. And Ch4 defect means there were a pair of cation and anion vacancy be created together. So always have the same numbers of vacancy for potassium vacancy and also the chloride vacancy. And the ion, the potassium ion and chloride ion be moved to the surface of these ionic materials. This is what we call a Ch4 defect. We have two vacancies with positive charge and negative charge be created in the same amount or same numbers. And the second mechanism is we call the Frankel defect, which means a pair of cation or anion self-interstitial defect and corresponding vacancy be created together. So we use a silver bromide as an example. Silver is a small black ball and the bromide is a white big ball. So here, in this case, we can observe the silver cation left its original location and moved to the interstitial defect. So it left a vacancy at the silver side with one negative charge. And the silver now was at the interstitial defect or self-interstitial defect with also one positive charge. So this is what we call a Frankel defect. So in ionic solids, there's a very important point of view you need to consider would be the electrical neutrality must be maintained. So here the electrical neutrality is maintained, right? Because we create the same numbers of cation and anion vacancy. And here also, right, we have a negative one and we also have a positive one. So finally we reach the electrical neutrality. Okay, so now you have some idea about how to have a vacancy formation mechanism in ionic solids. Then we want to show you how to name the notation in this ionic solid. Notation means how we point out or how we identify the location of your specific cation or anion or the vacancy, how to locate the ions or the vacancies. So that's a notation method. So how to name that? So A here, you can put here as the atom or the vacancy you are interested in. And the right upper side, you can you based on the charge state. If it carried with one positive charge, you use this dot to represent one positive charge. And if it have one negative charge, you use a one prong to represent the one negative charge. But if it remain neutral, then you use this cross to represent the neutral state. And the right bottom side is the site of the atom or site of a vacancy. Okay, so here just let's try to practice here. For example, here this is how to describe this vacancy. Is the vacancy, right? At where? At the potassium side. It was a potassium ion, right? But a potassium ion left or removed. So it was at, so this vacancy now is at the potassium side and with one negative charge. Because the potassium with one positive charge, right? Then potassium left, so the vacancy now will become one negative charge. So we got a prong here. So you can practice. You can observe there's a vacancy at here. So the vacancy at chloride side, and chloride have one negative charge, but this is a vacancy, so have a one positive charge. You use a dot here. And by the way, if you want to describe this chloride here, so I will say chloride at chloride side, and the charge state will be compared with chloride ion, so with is neutral. So for this one, is a chloride at chloride side with neutral. So potassium, if you want to describe the location, potassium at potassium side also with neutron. Okay, so now I believe you have some idea. The neutron actually is not means is compared with its original ion is not the total charge. The neutron doesn't mean that ion does not have any charge state. Okay, it's just compared with previous ion at that side. Okay, so this is what we call a neutron. Okay, so that's now you know how to name the atoms, the ions, and also the vacancies in the ionic solids. And you also know there are two vacancy formation mechanism in ionic solids, including the Schottky defect and Frankel defect. So I'm going to show you some examples here. We have some ionic materials in FCC. So we have a potassium chloride, sodium chloride, silver bromide, and all these ionic materials belong to FCC structures. So I just simply grab the sodium chloride as an example. If you take a look on the sodium ion, so it shows actually the structure is FCC. And if you put focus on the chloride ion, it also is FCC structures. So this is the FCC structures for sodium chloride. Okay, so now let's move to some real cases. So we have a potassium chloride ionic crystal with FCC structures, and we observe there's a Ch4 defect formed in these potassium chloride ionic crystals. So can you try to estimate or formulate the diffusivity of potassium ion or diffusivity of chloride ions in these ionic materials? So this is our purpose, right? And just to give you a quick review or hint here. So the diffusivity, the vacancy mediated diffusion, in that part, we know the self-diffusivity is equals to XV, the vacancy fractions, diffusivity of the vacancy, and also the correlation factor F. So in order to, based on this idea, you know that if we want to formulate the diffusivity of potassium ion and chloride ions, we need to know the vacancy at potassium side, the fraction, and also the fraction of chloride at the vacancy or at the chloride side, the fraction of vacancy at the chloride side, right? Because the VK and VL will change or will affect the diffusivity of DK and DCl, okay? And this is just a quick review. The vacancy fraction is equals to vacancy exponential negative vacancy formation energy divided by KT. This is a quick review for first sections. Okay, so now we know that because there's a Ch4 defect formed in potassium chloride materials, so when you try to formulate these reactions, so you can, before Ch4 defect formation, you can say potassium side with neutral charge plus a chloride ion at chloride side with neutral charge. But now we have a Ch4 defect form, right? It's a pair of VK and VCl. And the rest of part you also remain. You can also find K potassium at potassium side, chloride at chloride side. So you can delete these terms. So you can rewrite this equation to become here. Now means there's no Ch4 defect formation, and then will become you generate a pair of VK and VCl. So based on this equation, I believe you can write down the K equilibrium, the rate constant at equilibrium conditions will express like these fractions times these fractions. So so some people probably were curious about why this equation can lead this. So I give you I try to give you some detailed deviations. So none means we don't have Ch4 defects, right? Then we observe the Ch4 defect form inside our ionic materials. So I can write A become B and C, and this is a reversible process. And the forward rate constant K1 and the reverse reaction with a rate constant K2. So based on this is a reversible process, and when it reaches equilibrium conditions means K1 times concentration A will be equals to K2 times C times D. And what's the K equilibrium? Do you remember? K equilibrium actually is a K1 divided by K2. So K1 divided by K2, so you can put here, so you got C times D divided by A. And K1 actually is a rate constant. If just give you a quick review, rate constant is proportional with exponential minus activation energy divided by KT. So if you want to write down what's the K1, K1 is what? A to become C and D. So you got the K10 exponential energy barrier minus E1 divided by KT. And K2 actually is let's say CD to become A, right? So energy barrier is E2. So we express like a K20 exponential minus E2 divided by KT. So based on K1 divided by K2, so you got exponential minus E1 minus E2 divided by KT. So E1 minus E2 actually is this one will be the activation energy. And some people probably, when you find out this part actually is K1 divided by K2, but K10 divided by K20 won't become 1. So actually, let's still have some certain parameters here. Frankly speaking, you can put the K or something, some constants here in front of explanation term. But in all these sections, the textbook put more efforts on the temperature dependent terms. So some deviations you can find there's some parameters missing or some constants missing. So it's the reason for that. Okay, so you got the K equilibrium is exponential delta E divided by KT, and here to here the difference is we don't have a Ch4 defect and we have a Ch4 defect. So this will be E1 minus E2 delta E is a Ch4 defect formation energy here. And so here equals to here, K equivalent here, and C times D divided by A. C is a this times this divided by this. And this divided by this, instead of using concentration, here they use the fraction. So fraction VK, fraction VCL, and now we don't have fraction. We don't have a vacancy. We don't have vacancy form inside our ionic material. So this will be becomes to 1. So you got VK times VCL equals to exponential minus Ch4 defect formation energy divided by KT. Okay. So just remind you, the VK and VCL is not a concentration VK, it's a fraction of VK. This is a fraction of VCL. So let's take a look. The purpose here is you want to know the D star K, D star L, CL. So in order to understand the D star K, you need to know the X VK, right? So SVK actually is a VK prime. So as long as we know these values, and I can put here, then I can get the times the dV and F, then I can get the dK. So this is whole story. Okay, so in order to get the dK and dCl, so don't forget, Ch4 defect formation also need to obey the electrical neutrality. So the numbers of VK will be equal to the numbers of VCL, right? So VK equals to VCL. This is the fraction, okay? And equals to, because this equals to this, so you got a square term, and you take the root on both squares, so you got the 2 at the bottom. So now you know the VK equals to VCL and equals to this term. So we directly put this term back to here, so you got the dK star equals to XVK dK to dK and correlation factor F. And here don't forget, when you talk about the ionic materials, we usually will put the G here. The G is involved different crystal structure, different mechanism involved in these ionic solid materials. And the value for G is in between 1 and 2. And depending on different material systems, okay? So we just based on the equation we derive in first sections. So XV here is XVK. Because we talk about dK, so it will be XVK. And the dV, the diffusivity of a vacancy, the relationship between the VK and the potassium will be the diffusivity of potassium ion jump into the VK. So it will be this jump to here and times F. the same idea, right? And when you try to write down the anion diffusivity of anion chloride, also be G, XVCl, and the Cl here. Cl jump into VCl, diffusivity of Cl jump into VCl times F. As long as you can write down these equations, the rest of part just try to decouple or fill out each term. So what's the XVK? XVK is the same of VK prime, right? As I mentioned, it's a fraction of VK. It's the same, right? So just copy this term. It's a Schottky defect formation energy divided by 2kT. But this is a G, so we want to separate in entropy and enthalpy terms. So this term will be VK prime or XVK. And the diffusivity part will be the what? Will be, because this is FCC, right? It's FCC. So FCC, based on previous slide, you know, diffusivity for FCC is F A square mu, F A square mu, and migration energy. So migration energy separate into entropy and enthalpy term. C means cation jump into the vacancy. This is cation jump into the vacancy at the potassium side. And you fill out the G part here. And for diffusivity of anion chloride, so the same idea. XVCl is the same here, so you got this one. And also diffusivity is the Fa square mu, Fa square mu. Okay, and migration energy is anion jump into the V at chloride side, and the G put here. So when you talk about the diffusion activation energy for this ion, so potassium chloride materials with Schottky defects, then would be migration energy plus the Schottky defect formation energy, enthalpy divided by 2. And CV or AV, depending on what the diffusivity is, belongs to potassium ion or chloride ion. So this is the diffusivity of the potassium and chloride in potassium chloride ionic materials. And you observe some Schottky defects form inside, but please highlight there's no purity or no dopants inside this ionic material, so this belongs to intrinsic material property. Okay, but next I'm going to talk more about this is DK and DCl, but how about if I try to dope some dopant inside these ionic materials? Does this kind of behavior will affect the DK and DCl? If the question is like I explained, if I dope some dopant inside these ionic materials, I'm just curious about whether the DK change or not. So first thing come out from your mind will be the DK actually is proportional to XVK, DV, and F. So if the dopant will change the VK, the fraction of VK or DV, F usually won't change the F, right? So if the dopant will change the XVK or DV, then that will change the DK star for sure. Okay, so let's give us some examples here. If I try to dope the calcium with 2 positive charge in potassium chloride ionic materials by doping calcium chloride, so can you try to modify the DK star or estimate the DK star? How the DK star change after doping process? So first of all, we need to assume there's a Ch4 defect form inside this potassium chloride. And I try to dope the calcium chloride inside this potassium chloride materials. So the calcium with 2 positive charge will try to occupy the VK, the vacancy at potassium side. But the calcium has 2 positive charge, right? And this VK only have 1 negative charge. So you can get 2 minus 1. So you got 1 extra 1 positive charge here. So I got a dot here. So it means the calcium, the dopant calcium ion will at potassium side and now at this location with 1 positive charge. And the chloride always will locate at vacancy at chloride side, so remain neutron. And we have 2 chloride, right? And it will sit at chloride. And don't forget, as long as I have 2 chloride, and that will generate the same numbers of VK and VCl, right? So you will have 1 extra VK prong. So based on these descriptions, you know as long as I dope more calcium chloride, then I will have more VK prong. So on this idea, I will change the XVK. So the DK star for sure will change in the meantime. So doping calcium chloride will affect the fraction of VK, lead the change in DK star. So this is whole story. But how to quantitatively to understand how the DK star change after doping? So I need to do some calculations. So in order to reach the electrical neutrality, so all positive charge will be equal to all negative charge. So the positive charge will increase the calcium at potassium side with 1 positive charge, and also the vacancy at chloride side with 1 positive charge. And the negative charge one would be the vacancy at potassium side with 1 negative charge. Okay, so under these situations, we can get this idea. You can just ignore this part. Before dope, the VK prong square, pure means before dope. The VK prong square will be equal to after dope VK times VCl. This idea actually you learn from semiconductor industry. You know the Ni square in the carrier, the charge carrier Ni before dope. The charge carrier Ni square will be equals to concentration of N times concentration of P carrier, right? So the same idea, before dope VK prong square equals to after dope VK times VCl. And the VCl part we substitute with VK prong minus C calcium at potassium side with 1 positive charge. So this one, substitute this one. And now you know VK prong times VCl also will be satisfy the exponential minus Ch4 defect formation energy divided by KT. So based on this idea, if you take a look at these equations, you can get the VK, right? VK expressed like this. Just focus on this. This you can consider as a constant. So you got a VK prong square minus this one times VK prong, and you got a minus this term. So you got a VK prong equals to this one. The purpose here is we want to know how, the VK prong, right? As long as we know the VK prong, then we can know how the DK star change after dopant. So we got as a relationship between the VK prong and also the dopant. So based on this, we can simply classify our case into 2 extreme cases. The first one is if the VK prong VK prime pure means the before dopant. If this one is much larger than the the uh, the the concentration of the dopant, this one is quite large, and you can ignore one. You can take the root on this one and ignore this term. So VK prime will be equals to, take the root on this one. You can delete this term. So you got the VK prime would be equals to VK prime pure. So means after dopant, the vacancy at potassium site remain constant or remain the same with before dopant. So VK prime will be equals to VK prime pure. Before and after dopant, VK prime remain constant, which means the dopant is quite small. The concentration of dopant is quite small. So the property, we also under this situation, we also highlight this material property belongs to intrinsic material property. So based on this, VK prime equals to VK prime pure. So VK prime pure is a Ch4 defect formation energy and dVF. And however, if the dopant concentration is much higher than VK prime pure, this is quite large, and this term will be deleted. You got 1 plus 1 is 2, 2 delete this one. So VK prime will be dominate in proportion with the concentration of the dopant. So you will rewrote this term here, so got this results. So on this situation, the diffusivity would be dominated by the concentration of the dopant. On this kind of property, we call it is extrinsic material property. And based on this, we try to plot the log dk star versus 1 over t. Then under this situation, you know the slope will be included this term, a temperature dependent term, and this one, because we know the dopant, the concentration for the dopant, this is big constant, so you got the only one term related to temperature. So you got two slope here. The first one is the slope will be this term, right? Will be enthalpy term, will be included the migration enthalpy HM and also the HS divided by 2 will be proportion with this one. And for the extrinsic one, because this is constant, so the only term here will be the vacancy migration enthalpy. Okay. So based on this, you can have idea. As long as when you measure the decay at a different temperature and you try to plot the log dk versus 1 over t, then if you got this curve implying that there are two mechanisms co-dominate into your temperature regime, your interesting temperature regime. And after fitting, then based on the results for the fitting, you can know the vacancy migration energy. And after fitting, you know the slope, right? As long as you know this term, you know the slope, so you can estimate the Ch4 defect formation energy in these material systems. Okay? So this is the provided you a method to estimate the vacancy migration energy and Ch4 defect formation energy in your ionic materials. Okay. If you focus on the temperature as this temperature, and if there's a two because in your interesting temperature regime, right, and there are two different material property dominate, which included intrinsic and also dopant effect, right? So this diffusivity at this temperature regime actually is a summation of this intrinsic material property and also the dopant effect. You sum this and this, you got this data point. But at this the temperature at the higher temperature region, you can observe the intrinsic material property will override on dopant effects. But at a lower temperature, we can observe under this situation, if you continue the intrinsic property at this region will be quite small, right? So this region, temperature region, was is a dopant dominant. So as long as based on this, as long as you measure the divisibility decay at different temperature and plus the log decay star versus 1/T, and you got two slope, so you can directly know that during your interesting temperature region, they are for sure there's an intrinsic and dopant effect co-dominate or coexist in your material system, and which mechanism dominate, you will depending on as long as you after fitting, then you can say that, oh, okay, but higher this temperature, then it's intrinsic dominate, and lower this temperature will be dopant dominate. Okay, it will be we can discuss this in based on different material system, the temperature to separate intrinsic dominate and dopant dominate will be different. Then we already finished the Ch4 defect part, right? And how about the Frankel defect? So as we mentioned before, we use the silver bromide as an example. And what's the Frankel defect? Do you remember? No matter is a cation or anion, moved or leave its original site and to be an interstitial site, to be an interstitial defect, and left a vacancy. This kind of situation we call a Frankel defect. And based on no matter is experimental observation or literature, in silver bromide system, we observe the cation silver. Silver diffusion is based on the interstitial mechanism, which means the silver will leave the silver side to be an interstitial defect and left a silver vacancy at silver side. So you can directly write down this chemical equation. Before Frankel defect formation, silver was at the silver side with neutral charge. But after Frankel defect forms, silver was at the interstitial side with one positive charge, and it left a vacancy at silver side with one negative charge. So based on this equation, you can write down the rate constant under the equilibrium condition will be fraction this one times fraction this one, and equals to Frankel defect minus exponential minus Frankel defect formation energy divided by kT. And due to the electrical neutrality, which means we have this one, and also have an even number, the same number of silver ion and the vacancy at silver side, so this will be equals to this one. So we got the fraction for this one, and this one will be equals to minus Ch4 or Frankel defect formation energy divided by 2 kT. As long as we know the fraction, so we can simply write down the divisibility for silver and also the bromide. For the silver will be X will be G, and also because silver will become become the interstitial defect, so will be Di. We need to know the divisibility for this interstitial defect and also the fraction of interstitial defect times F, and G is due to this is ionic materials. And for bromide, how the bromide move in this? Bromide is a bigger one, right? How the bromide moved in this ionic materials? The only possible is the bromide probably have very little probability to jump into a vacancy at the vacancy at silver side. So will be XV, the bromine jump into the vacancy at the silver side times the F. But as I know, the diffusivity for this term is quite small. Okay, but this is the only way that the bromide can diffuse through these ionic materials. So when you finish this one, you can express, fill out each term, right? Regarding to the fraction of interstitial defect will be depending on the Frankel defect formation energy, and the diffusivity for these interstitials will be the same, right? It's a migration energy, and migration part will be the cation move to interstitial side, and also the times the G. And just remind A squared mu due to the FCC structures. And the bromide one, the vacancy formation energy, the vacancy will be silver vacancy formation energy, and the bromide jump into the vacancy part will be the anion jump into the vacancy at silver side will be the migration energy, and the rest of part is the same. So for the diffusion activation energy, the one we just talked about is a temperature dependent term, will be included the Frankel defect formation energy and plus the migration energy. Either is the migration energy of silver jump into the interstitial side, or the migration energy about the bromide jump into a vacancy at silver side. Okay, so today we ended here.